Hello everyone. So today we are going to solve questions using Existence and Uniqueness Theorem. Okay. So this is our first question and it says for initial value problem y prime equals 2y over x when x is greater than 0 and 0 when x is equal to 0 provided with the initial condition y0 is 0, right? Show that the Lipschitz condition is not satisfied in any closed rectangle containing 0, 0. That means this initial condition, right? So we have to show that around this point our Lipschitz condition is not satisfied. Okay, so we are taking y1 and y2. Why? Because you know that while we uh, check the Lipschitz condition in our initial value problem, we have to calculate our fxy at two different points, right? So that's why we are taking y1 and y2 as 2 points, and we are solving the left hand side first of the Lipschitz condition. Okay, so mod fxy1 minus fxy2 over mod of y2 minus y1. Okay, now fxy1, this is the this is fxy when x is greater than 0. Okay, so we are taking this condition right now. Okay, so now fxy1 will become 2y1 over x, right? We have to put these values in fxy. So fxy1 will become 2y1 over x, and similarly fxy2 will become 2y2 over x. Now modulus of fxy1 minus fxy2 becomes 2y1 over x minus 2y2 over x. Now here we have y2, modulus of y2 minus y1 in the denominator, and it will remain same here. Now you can see that 2 over x is common in both these terms, right? So we'll take it out. So I took 2 over x here, okay, and remained with only modulus of y1 minus y2, and in the denominator we had modulus of y1 minus y2, right? So you can see that these two terms are same. That means these will get cancel out, right? And we left with only modulus of 2 over x. Now I removed this modulus. Why? Because you can see that 2 is a positive integer, and here x, we are taking x as greater than 0, right? So that's why I removed this modulus from this term, right? So it becomes 2 over x. Now 2 over x can be made as large as we please by choosing sufficiently small values of x. You can see that as x tends to 0, this term will tend to infinity, right? Therefore, there exists no such n which is independent of x and y such that modulus of fxy1 minus fxy2 becomes less than n modulus of y2 minus y1. Okay, because as you observe that as we were putting the smaller value of x, we were getting a larger term, right? So that means this Lipschitz condition is not satisfied there, right? So Lipschitz condition is not satisfied in any region containing y equals 0, and hence it is not satisfied in any closed rectangle containing 0, 0. Okay, and this is what we have to prove. Now here is the another question that says show that fxy given as xy square. First, we have to show that this function satisfies a Lipschitz condition on any rectangle x. In this rectangle, x lies between a and b and y lies between c and d. Okay, here A and B are included, and here also C and D are included. So we have to first show that this function satisfies Lipschitz condition on this rectangle. Okay, this rectangle contains the point xy such that x lies between A and B and y lies between C and D. Okay, so here fxy is xy square, right? And the derivative of this function with respect to y will be 2xy, right? But we have to check Lipschitz condition here. So we'll try doing that. Here you know that while solving Lipschitz condition, we try solving the left hand side first, and then we make it less than equal to some constant, right? So we are solving it first. Fxy1 will be, this is fxy equals xy square, right? So fxy1 will be xy1 square, right? We have to put these values in here, this fxy. So fxy1 becomes xy1 square, and similarly fxy2 becomes xy2 square. So modulus of this fxy1 minus fxy2 will become modulus of xy1 square minus xy2 square. And in the denominator we have y1, a modulus of y1 minus y2, right? So it will remain same. Now here you know that x is common in both these terms. We'll take it out. So we took it out here, and we're left with y1 square minus y2 square, right? So y1 square minus y2 square will become y1 minus y2 and y1 plus y2. Now you can see that these two terms are same, y1 minus y2 and y1 minus y2. So these terms will get cancelled out, and we left with only modulus of x and modulus of y1 plus y2. Right? Now you know that the rectangle contains the point x and y, x comma y, such that x lies between a and b and y lies between c and d. That means the value of x cannot be greater than b and cannot be smaller than a. Similarly, the value of y cannot be greater than d and cannot be smaller than c, right? So we have a limit for both these points, right? That means we will be able to find a constant such that this term will be less than equal to that constant. Okay, so that's why we can say that this term will become less than equal to n for the condition that is given to us. Okay, for x in between a and b, and for y in between c and d. Okay, so our Lipschitz condition gets satisfied for x for the rectangle having the points x comma y such that x lies between AB and y lies between C and D. Okay. Now the second point says that show that this function does not satisfy the Lipschitz condition on any strip. Okay, so here we are not given a rectangle, but we are given a strip such that x lies between a and b and y lies between minus infinity to infinity. So here we are not given a rectangle but a strip. So if you try plotting this, here you can see that x is in between any two values, right? But y is not defined in between any two values. Y is ranging from minus infinity to infinity, right? So it will look like something like a strip, because y is not bounded. Okay, y can go to minus infinity and infinity also, but x is fixed in between a and b. So it will something like it will look like something a strip. Okay, So we have to show that the Lipschitz condition is not satisfied on that strip. Now, you know that when we solved this Lipschitz condition, we got this, right? And you know that y here is not bounded in between any two values, right? So we can take any value of y here, right? And as we take the bigger values for this these y1 and y2, this term will become bigger and bigger. That means we'll not be able to find such n that so that this term becomes less than equal to that constant. Okay. So here you can see that Lipschitz condition is satisfied for any rectangle containing xy points where x is in between some fixed value and y is also in between some fixed value, right? But it is not satisfied for any strip where x is fixed but y can take any value between minus infinity to infinity, right? So that's all for today. I hope you understood these examples, and in the next lecture we'll start with linear differential equations. Okay, that's all for today. Thanks for watching.